All right, type 3. We're going to up it just a touch. So what we're going to do in type 3 and type 4 is calculate the equilibrium concentrations. So we know that a chemical system is either at equilibrium or it's going to shift left or right to reach equilibrium. That's what we talked about in type 2. So if your trial KEQ is not equal to KEQ, then your reaction will shift left or right until you get to that KEQ value. What we're going to use now is math to determine if we know the initial concentrations, then we know what the equilibrium concentrations will be given certain scenarios. And in type 3, the scenario will be that the question will ask you for one or more equilibrium concentrations and maybe KEQ, but most importantly, it's going to give you the initial concentrations of all your species, and then it's going to give you the concentration of one of your species at equilibrium. Now, it could give you two, but it's kind of like giving you one. Okay, so the key idea here is that because one species is going to be known initially and at equilibrium, you're going to be able to calculate the change in concentration that it went through as it approached equilibrium. Now, I do have 6 steps here. They're a little bit loose steps, but I'll try to talk through them as I go through this first example. So in this first example, I have nitrogen and hydrogen making ammonia. What's going to happen is the question says some hydrogen and nitrogen are added to a container so that initially the concentration of nitrogen and hydrogen is, and then at a certain temperature and pressure, the equilibrium of hydrogen is found to be. So what they've given you here is the amount that was put in the container to react. That's your initial concentrations. And then they let it sit until it reached equilibrium. And then they've given you an equilibrium concentration as well. The steps to follow or to solve these type 3 questions are, first step, to make a rice chart. A rice chart is something that we use anytime that we're comparing initial to equilibrium concentrations. So we haven't needed this yet because in type 1, all they gave us was equilibrium concentrations. In type 2, they sort of gave us initial concentrations only, although it wasn't necessarily initially. It was more like at time t. But they only really gave us one row. In type 3, they're going to give you some combination of initial concentrations and equilibrium concentrations. So to set up a rice chart, the way that it works is R stands for reaction. So we've got nitrogen and hydrogen forming ammonia, and you write the reaction in the top. And then I is for the initial concentrations. So in this question, they're telling you that hydrogen and nitrogen were initially put in the container. They were put in the container so that there was 0.32 molar nitrogen and there was 0.66 moles per liter of hydrogen. Those are my initial concentrations. So I'm on step 2 here. Step 2, I'm listing my initial concentrations. Now there's a nice little like follow-up fact for this, which is that because this is initially, I'm telling you that we're putting nitrogen and hydrogen together to react. That's how much nitrogen, that's how much hydrogen. It's not in a mole-to-mole ratio. It's just the amount I've thrown into a container. One of them might be a limiting reagent. But the key thing is that because I'm throwing these together, there is no product to start. So when your initial time is 0, you're going to have a certain amount of reactants and no products. Or maybe you start with product and then you'd have no reactant. Then they will also give you one species, maybe 2, concentrations at equilibrium. So they've told me at equilibrium, the concentration of hydrogen is 0.30. Okay, so that's steps 1 and 2. So then step 3 is where we want to figure out how much our species have changed by. Now, this is a theoretical idea. Sorry, I just had to take off some headphones. So what it is that we want to figure out what the change is. The change is the only thing that happens in a mole-to-mole ratio. So you can put X amount of nitrogen and X amount of hydrogen into a container and they don't have to be mole-to-mole because I'm just putting that amount in. One of them is going to limit the reaction. At equilibrium, it might not be in a mole to mole ratio because I put different amounts of the species in to react. But the change line is your reaction actually occurring. And this happens in a mole to mole ratio. Now, I'm starting with nitrogen and hydrogen. As my reaction proceeds, I'm going to use up the nitrogen and the hydrogen, and I'm going to produce ammonia. So I'm going to decrease my amount of nitrogen and hydrogen and increase in amount of nitrogen or ammonia. This change is going to happen in a molar ratio. The nitrogen is going to go down by 1 molar amount. The hydrogen is going to go down by 3 molar amounts, and the ammonia is going to go up by 2 molar amounts. So I say that X is equal to 1 mole of change. So it's in a ratio of 1 to 3 to 2. So that at equilibrium, my concentration of nitrogen is going to be 0.32 minus some amount X. The hydrogen, they gave me the amount. And then my ammonia is going to be the 0 plus the 2X amount. So to be able to find the concentration of nitrogen and ammonia at equilibrium, I need to know what the change is. Because they gave me the amount of hydrogen at equilibrium, I have a full equation here. 0.66 minus 3 molar amounts, or 3x, is going to equal the 0.30. Then we just solve this like we would a linear equation, so I minus 0.066 from each side. I end up with negative 3x is equal to negative 0.36, and then I divide both sides by negative 3, and I end up with x is equal to 0.12. So I know that 1 molar change is going to be 0.12 moles per liter. So that if I wanted to calculate the concentration of nitrogen at equilibrium, it's going to be that initial amount of 0.32 moles per liter minus 1 molar change, which is going to be 0.32 minus that 0.12, which tells me my concentration of nitrogen at equilibrium is 0.20 moles per liter, or molar. To calculate the concentration of ammonia at equilibrium, it's going to be 0 plus 2x, or just 2x, which is going to be 2 times that 1 molar change, and it's going to be 0.24 moles per liter, or molar. So then if I wanted to solve for KEQ, KEQ is the concentration of products, which is my ammonia squared, divided by reactants, so nitrogen times hydrogen cubed, and then I can put in my equilibrium concentrations. So my ammonia was 0.24 squared, my nitrogen is 0.20, and then my hydrogen is 0.30 cubed. Then I plug this into my calculator. I get 0.24 squared divided by 0.2 divided by 0.3 cubed is going to give me 10.6 repeating. Then I look at my sig figs. Because I've got 2 divided by 2 and 2, I'm going to answer as 11. And again, equilibrium constants do not have units. So my KQ for this reaction would be 11. All right. You know what a good follow-up question would be for this? Is to calculate your Q original and then determine which way it shifted, right? Which went up, the products or the reactants? Ooh, that would be a good one for later. All right, but I have one for you to do. I'm going to start helping you set this one up, and then I'm going to say pause the video and give it a go. So the first thing here is that let's read the question. Suppose 4 moles of HI is placed in a 2-liter flask. This is initially. So when you're placing it in a flask, that's how much you're initially placing in to react, to produce hydrogen and iodine. At equilibrium, the concentration of iodine and hydrogen are found to be, what is the value of KEQ? So they've given me the amount of HI that was placed in initially, and then they've given me the concentration of hydrogen and iodine at equilibrium. that leads me to wanting to make a rice chart. So when you make a rice chart, I specifically didn't put one in here because I know sometimes when you see them so pretty, like the last one was drawn, they seem overwhelming. So what I do to draw a rice chart is I literally put RICE, I don't write all the words, and then I put a line beside it. And then in this reaction, I have HI, gas, making and remaking hydrogen gas and iodine. They didn't give me a reaction, so it's my job to make sure this is balanced. So I'm going to put a 2 out here to balance the equation. So the HI is my reactant. So as part of my reaction, I put 2HI, and then it's going to produce hydrogen and iodine. Now, instead of doing all these fancy lines like this one had with the plus sign and the arrows and leaving all that space, what I like to do is just separate my reactants from my products with a double line. So I know that this left-hand side is my reactants, and then I separate my products just with a single line. So the double line to me is like the arrow, and then the single line is like having a plus sign, just to make these seem less overwhelming. If you wanted to, you could throw like the little arrow in here, you could put another line in here, put a plus, but personally I like to keep these as simple as possible. So now what I want to do is I want to put in my initial concentration. It says that I put 4 moles of HI into a 2-liter flask. So the first thing I have to do is find the concentration of HI, right? Find the concentration, it's going to be mole divided by volume. So it's going to be that 4 moles divided by the 2 liters, which is going to give me the concentration initially of 2.00 moles per liter. So my initial concentration of HI is 2.00, which means that if I placed HI in the flask to start, there was no hydrogen and no iodine. Then I also want to put into the chart what my equilibrium concentration is. Now for this one, they gave it to me for both iodine and hydrogen, and they said at equilibrium, the concentration is 0.214. Step 1, step 2. Step 3 is to fill in your change line. So again, reactants decrease, products increase. They increase and decrease for a mole to mole ratio. The change line is the only line that we use a mole to mole ratio in. So the HI is going to go down by 2x, and both the hydrogen and the iodine went up by 1x. Step 1, step 2, step 3. Step 4 is to solve for x. Now I often will also fill this out. So the equilibrium concentration of HI would be 2.00 minus 2x. Then I'm going to calculate x. So for either the hydrogen or the iodine, 0 plus x gave me the 0.214. So I know that x is 0.214. There wasn't even any math I had to do. But to calculate the concentration of HI at equilibrium, you would do the 2.00 minus the 2x values. We said that x is 0.214. So then the concentration of HI at equilibrium is 2 minus 2 times 0.214, which is 1.572. Now technically, because we're subtracting, we're only keeping 2 decimal places of precision, but we're not going to round until our final answer. So we're going to keep track of our sig figs and our precision as we go, but we won't round till the end. The last thing they've asked me for is KEQ. So my expression for KEQ is going to be hydrogen times iodine divided by HI squared. So my concentration of hydrogen is 0.214. Concentration of iodine at equilibrium is 0.214. And then my concentration of HI at equilibrium is 1.572, but keeping track of my sig figs, and that value gets squared. So plugging into my calculator, 0.214, I'm just going to do squared, or times 0.214, divided by 1.572 squared equals 0.0185 to 3 sig figs. So this equation this reaction has not happened to a very relatively far extent because my reactants are so much greater than my products, and my KEQ is tiny. All right, hopefully that feels good, and then we'll start type 4.